Namaskar, my dear friends. Let us talk about voltage translator or level shifter, it is also called as. So, we'll try to understand why voltage translators are used. Let us say we have to have a voltage of here, let's say 3.3 volt, and we need output side 5 volt. So, there are two kinds of devices. Let us say we have host and we have target. So, what happens is this host voltage is giving you a signal of, let us say 3.3, 0 to 3.3, and we need a little bit higher voltage or maybe a possibility of little bit lower voltage also. Let's say 0 to 1.5 volt we need. Then what will you do? So there will be a device which will be used in the middle, which will be called as voltage translator or level shifters. These are mostly used in a lot of application. Let us say I2C application, or like LCD drivers or TVs, or we have gate drivers. So there are several occasions where you need to have this kind of voltage translators. So what is a voltage translator? As I already mentioned you, let us say we have a block which will translate the voltage from one level to another level. Okay. As I told you already, like let us say we have a signal coming from my microcontroller, which will give you either 0 volt or 3.3 volt. I'm always giving you a pulse wave, but it can be just one or two states. Let's say just it is low state and it is high state. That's all. Or it can be another way. Either it can go ahead with from high to low state. So this is my high, this is my low state. However, this low and high will be defined by the microcontroller GPIOs logic levels, which can be like 0 to 3.3 volt. Now let us say we need output side 0 to 5 volt, or it can be other voltages also. Let us say we need 1.5 volt or 1.8 volt or 2.5 volt, any other logic levels we need at the output side. Then what will happen? Basically what I am trying to tell you is, let us say this is my input side and this is my output side. Okay. So this is the block that will help you to do that. What happens basically is, let us say we give here a power supply of 3.3 volt because it is 3.3 volt, and we take a power supply here 5 volt. So 5 volt if you supply here, the logic level will be shifted to 5 volt. So that's the amazing work that is done by translator block or the voltage translator or the level shifter. The other way also can be done always. Like let us say we have the input voltage from microcontroller, or let us say some of the target signals. Let's say it can be RS232 signal, RS232 signal, or RS485 signal, or like I square C signal. All those signals are there. So this input can be of 5 volt logic levels, and we have to convert it to 3.3 volts. So that's the main understanding we should have, what kind of translator block that we should put. Okay, it must be compatible of changing one level of the voltage to another level of voltages. And this is very useful in case of like these days lot of miniaturization is happening, where we are shifting to lower logic levels. Earlier we were working quite frequently with 5 volt or 3.3 volt, but these days all the GPIOs have almost started giving you a logic level of 1.8 volt or 1.5 volt even. Okay, if you talk about FPGAs, then they are reaching up to around 1 volt also very easily. So what we'll do in this session is we'll try to understand these particular functionalities, or one of the example that we'll take from one of the IC, and we'll try to understand what are the different features and different circuit design that we should have into our account. So let us take one IC I'm taking from Nexperia, which is 74LVC1T45. So 74LVC1T45 is dual supply, 1 bit voltage translator. So dual supply means this is the block. So one supply will be this side, let's say VCCA, and another supply will be this side, which is VCCB. So either you can utilize this as input and this as output, or it can be this can be input and this can be output. So it can be a bidirectional or unidirectional. Okay. So what are the benefits and features of this particular IC? I'll just tell you. Same way, same methods you can extend it to another ICs, or there are ample number of like ICs that are there in the market. I'm going to talk about Nexperia right now. Nexperia, But we have a lot of other manufacturers for voltage translator. Let us say analog devices, which is having a combination of like maximum integrated linear technology, all those things. We have Texas Instrument, we have Renesas, and you know like SS. Okay. Then we have like microchip. We have Infineon Technology, we have onsemi. Lot of manufacturers are there. Okay, so let's talk about stick to this particular understanding, like what are the features and benefits of this particular IC that we have taken into account, and the same thing can be extended to other manufacturers ICs as well. Okay, so you can see it has very wide voltage ranges, it has low propagation delay, it has low power suspend mode also, like let us say we have low power, then it can go to suspension. It has auto direction sensing. Then it has three tri-state output option. It has voltage tolerant option. It can be utilized in lot of application like I2C lines or cell phones or LCD TVs or like a stub or personal computing as well. So what is the logic diagram or logic symbol that looks like? So let us say this is my A, which is let us say my input side, and this is B, which is my let us say output side. It can be changed, it can be another type, like it can be input and it can be output based on the direction that you are setting. Okay, so what happens is we have VCCA, that is supply voltage at A side, and we have VCCB, that is supply voltage at B side. And what is happening is based on the direction, this logic level will be propagating through B side and shifting the logic level. Okay, so let us say we have input of 0 to 3.3, it can shift to 0 to 5 volt based on the supply that you are giving here. Okay, so we'll understand that also. So the supply, it will depend like what is the output logic level that you want it. Okay, so what are the features and benefits of this particular IC that we'll talk about? So it can take up A side as well as B side both from the voltage of 1.2 volt to 5.5 volt. Okay, so the benefit that I am going to talk about from this particular session is you can utilize the same ICs also in your lot of application, and at the same time you will have an understanding of what is voltage translator and how these are generally utilized in circuit designs. It has very high noise immunities. It is having very good maximum data rates are there. Like you can see from 3.3 volt to 5 volt translator, it can go up to 420 Mbps. And if it has to translate to 3.3 volt from any other voltage levels, then it will be working up to 210 Mbps. So like that, you can have another things. Okay. If it has to translate to lower voltage level, then you can see the speed is actually a little bit decreasing. So it happens because of the low level logics like 0 to 1.5. It is the data rate decreased a little bit. Okay, uh, according to this particular IC that it is taking. Coming back to, it has suspend mode, it has latch up performance exceed 100 milliampere per ZESD 78 class 2. It can give you an output volt, drive up to plus minus 24 milliamperes of current rating. Okay, so it has a capability of giving you per channel 24 milliamperes. Input accepts up to 5.5 volt, that I already told you. Okay, and the power consumption is 16 microampere maximum ICC, so it is not going to take more than 16 microampere from the VCC pin. Okay, and it has I-off circuitry, provides partial power down mode operation also. Okay, continuing the features, we have another things like ZEDC standards are there, which are having 1.2 volt to 1.95 volt, 1.8 volt to 2.7 volt. Basically, this is going to work with 1.5 volt logic, with the 1.8 or 2.5 volt logic. This is 3.3 volt logic, and this is 5 volt logic. This is how the setups are. Like this is for 1.5 volt, this is 1.8 volt or 2.5 volt, this is 3.3 volt, and this is 5 volt logic. Okay. You can see a human body model like HVM is going to exceed up to 4000 volt, and CDM is exceeding up to 1000 volt of ESD protection. It has multiple package options as well, and it can work from minus 40 degrees centigrade to 85 degrees centigrade. and minus 40 degree centigrade to 125 degree centigrade. So there are two uh, temperature available. Coming back to the part number example, so it has like TSSOP package or Exon package, XSON package. Okay, so XSON package are very small package and TSSOP package are with pinout packages. So you can see we have two part number. One is with LVC and another is with LVCH. How do you decide the part number? Based on the number of bits or number of channel that is available. So it is telling 7 for LVC1. Okay, similar to that, if you have to have two channel, then 7 for LVC2 will come. Another version will be less 7 for LVC4, 7 for LVC8, like that it will keep on increasing, and that's how you can make it a general part numbers. All right. Let's talk about the pin configuration. So let us say this is the IC that it looks like exactly in TSSOP 6 package, and you can see we have VCCA pin which is going to have a supply voltage port A and direction also. Okay, so direction will be set by this VCC A side voltage level. It should not be connected to VCC B side voltage levels. Okay, coming back to the GND, so this is ground level pin. We have A, which can be a data input or output. So this A pin will be having data input output, B pin will be having data input output. So it can be acting as input, this will be acting as output. And at the same time, if it is acting as input, then this will be acting as output. Understood? So this is the direction setting that will be done. So direction control is done by DIR pin. So what happens is, if you ground it, let us say you connect it to ground pin, okay, then what will happen is it will go from A to B, A to B. Understood? So direction is 0. If my direction is set to 1, that is high logic level, let us say we are going to connect this direction to my supply voltage. Okay, so in that case this will become high, and in that case my channel will start from B to A. I will show it to you, it is written in the data sheet as well. Okay, coming back to the next part, what happens is function table. So how this function works? So as you can see, we have VCCA and VCCB supply voltage ranges, which is going to take it from 1.2 voltage level to 2.5 volt level. Okay, now as I told you, input output and how it is working as. So let us say direction is set to low. So what is telling is, if direction is low, like it is ground, then A will be equal to B, and B is working as input. B is input. Similar to that, if direction is high, then A is working as input and B is working as output. So B will be equal to A. So the thing what I told you here is just opposite. Okay, so when it is ground, like direction is low, then A will be acting as output. Okay, and B will be the input. So this is how, it's nothing but it is very simple to understand, like based on the direction pin setting, whether it is low or high, what will be the input and what will be the output. So as you can see, B is acting as input, and whatever the value of B is there, that will become A whenever direction is set low. And one more thing that you can see is whether my VCC A or VCC B, any one of them or both of them are low, okay, are low, or voltage is not given, then IC will not work. It will go into suspend mode or it will go into shutdown mode. So you have to make sure the voltage level is available in both the pins with the VCC A as well as VCC B. There is very good thing that is called also as, like limiting values or absolute maximum ratings of any IC that you have seen. So absolute maximum rating of supply voltage are up to 6.5 volt. Okay, the input clamping current that it can take up to 50 milliamperes. Okay, then input voltage, as I already told you, like since the supply voltage is going up to 6.5, so input voltage allowed at port A and B both are up to the same VCCA voltage level. Okay, you can see output voltage level that will go like whether it is high or low. So that will also go up to VCCO plus 0.5 volt. So VCCO is actually nothing but going to be equal to your output voltage of logics. Okay, and this output voltage logic is actually taken by based on the supply voltage that is given to the IC. Coming back to the output current, so output current that will be there in each of the channel will be up to plus minus 50 milliampere, but this is limiting value, you will not be getting this much. We will be seeing the recommended values as well, and this is all about this particular understanding. We have total power dissipation across this particular IC is 250 milliwatt. Okay, and as you can see, we have ground current which is going to up to minus 100 milliampere. So what happens is, actually this is the current that is going to limit the overall capacity of a complete channel. So right now I'm going to talk about single channel, which is going to be A to B. Similar to that, we will have multiple channel as well, and in that case all those put together we will be having a current capability of 100 milliamperes only. Okay, let's talk about recommended operating conditions. So this was absolute maximum ratings or limiting values. Once we talk about recommended ones, so you can see supply voltage is limited to 1.2 volt minimum to 5.5 volt maximum. Okay, so you can work with, let's say, 3.3 volt logic very easily, or 5 volt logic very easily. Similar to that, we have input voltage which is going to come into the parts of like A and B inputs, where we are going to give the PWM signal, or maybe logic signals, like logic signals. So that will be taking up to 0 to 5.5, whether it can be 0 or it can be 5.5. Output voltage level is going to take up to active mode, it will be 0, or otherwise VCCO, that is output voltage level of high logics. Now coming back to the transition time, which is rise time and fall time. So what happens is, as you go on little bit of higher voltage levels, you will see the 5 nanosecond per volt, and similar to that for VCCI it is taking 20 nanosecond per volt. So as we are going to have higher voltage level, our delay will increase a little, because it is taking 5 nanosecond per volt. So for 5 volt it will take 25 nanosecond. Understood? So this is how it will work out. Let us talk about static characteristics that we have just now seen. So what is this static characteristic is, what is my high level input voltage? So let us say our input voltage is our input logic input is A. Okay, so this A terminal, it will be let us say our working voltage is 1.2 volt logic level. Then if you have to give a high, then it has to be minimum 0.8 times VCCI. What does it mean is, what does it mean is 0.8 multiplied by 1.2, that is बराबर 0.96 volt should come, then only it will consider as high. Okay, this is how it will be considered. Similar to that, you have, let us say, input voltage between 1.4 volt to 1.95 volt. Let us say 1.5 volt you are going to give as input voltage towards A side. Then if it is 0.65 times VCCI, then only it will consider as high, otherwise it will not. Similar to that, you have VCCI 3 to 3.6 volt, let us say 3.3 volt logics. In that case, minimum you have to give 2 volt, then only it will be considered as high. Okay, so this was all about similar to that, for 5 volt you can see 0.7 times we have to give VCCI, otherwise it will not consider as high signal. Similar to that, when it will consider as low signal, so let us say my input is A, and we are going to have here it was, let us say, high, then here it is, let us say, low. Okay, this is, let's say, low, this is, let us say, high we have. So for VCCI logic 1.2 volt, this must be less than like 0.2 volt of VCCI, 0.2 times of VCCI. So you should not give more than this, otherwise it will be like in the noise margin range or something. So let us say you are working with 1.2 volt logic levels. In that case, what will happen? 0.2 times 1.2, so that is going to be 12 दूना 24, 0.24 volt maximum. So you have to give maximum to 0.24 volt, then only it will consider less than low logic level, otherwise it will be in unknown condition. So now you can see, for 1.2 volt logic level, high will be considered for the voltage inputs more than 0.96 volt, and low will be considered for the inputs less than 0.24 volt. Understood? So let us say we have 0 and 1.2 volt. So my low logic level will be here and high logic level will be here at the input side. So my low logic level must be less than 0.24 volt and my high logic level must be more than 0.96 volt. Understood? So all signal above this voltage level will be considered as high and all signal below this will be considered as low. That's the main understanding you should have. And between this, any input you give, it is not going to decide whether it is low or whether it is high. Understood? So this is the main understanding. Similar to that, you can configure the same analysis for 3.3 volt logic. What is the value of high and what is the value of low? So it is telling you 2 volt and 0.8 volt. So let us say we have 0.0 to 3.3 volt logic. So in that case, there will be a high and there will be a low. So 2 volt and this will be 0.8 volt. Understood? So for higher than this will be considered as high and lower than this will be considered as low. So that's the main understanding about this. Okay. Hope you have a very complete idea about this particular low logic levels and high logic levels at the input side. Similar to that, we have output side. Okay. So output should also be recognized, right? So we have the IC which is having input and which is going to have output. So output should also be considered whether it is high or low, right? So whether when it is high or when it is low. So based on that, voltage levels we'll try to understand. So let us say output. Okay. So we have output. So this is actually your minimum and this is maximum and this is also minimum and maximum at 125 degree centigrade. So this is at 125 degree, this is 25 degree centigrade. So when it is going to consider as high logic level, so high logic level must be, VCCO is, let us say 1.2 volt to 4.5 volts. In that case, what will happen is, this must be minimum VCCO minus 0.1 volt. Otherwise, it will not be able to consider. Okay. And similar to that, let us say for VCCO 2.3 volt logics, it must be 1.9 volt minimum. Then otherwise, it will not considered as high. So high, to get high, it has to be minimum getting at the output of 1.9 volt. For low logic levels, let us say for 1.4 volt, we'll talk about this only, 2.3 volt logic only. So 2.3 volt, maximum you have to get 0.3 volt to consider it as low. Otherwise, it will consider them nothing. So this was high, minimum 1.9 volt we should get, and maximum we should get 0.3 volt to get a low. Understood? Or to consider it as low. Hope you are very clear about this. If you are working with 3 volt logic or 3.3 volt logic, in that case, maximum 0.55 volts should you should give or you should get at the output to consider that voltage logic level as low logic level. And similar to that, for 3 volt logic levels, high side you have to get minimum 2.4 volt to consider it as high logic level. Now let us talk about dynamic characteristics. So some dynamic characteristics are there. It is nothing but what is the propagation delay from low to high or high to low. So low to high is TP, like propagation delay low to high, LH. Okay. Similar to that, propagation delay high to low is TP, HL, high to low. Understood? So the condition that is given right now here is we have VCCA as 1.2 volt. Okay. So similar to that, there will be tables for 1.5 volt or 1.8 volt or 2.5 volt, 3.3 volt, 5 volt. All those different values we will be having different tables. Okay. So VCCA is 1.2 volt and VCCB is considered to be almost all the voltages you can see, like 1.2 volt, 1.5 volt, 1.8 volt, 2.5, 3.3 and 5 volt. Okay. Now the propagation delay that it is coming up is, you can see for 1.2 volt logic outputs we are going to get 10.6 nanoseconds. Okay. And as we want to have little bit higher voltage logic level on the B side, let us say 5 volt, then my propagation delay has decreased to 5.1 nanosecond. Okay. So similar to that we have for B to A also. So from B side you are giving the input, then A side it will be like flowing as the output, and the same way we have little bit more delay compared to A to B. So A to B is bit faster compared to B to A, but there is no significant change. If you are not bothered about nanosecond delay, then it is very good IC to proceed. Similar to that, we have like propagation delay for YouTubers for low to high, then high to low, and similar to that, other personal, functionalities are there. So let's try to understand this with a diagram. So let us say what happens is my A is input and B is output. So let's say A is input, which is going to high to low, high to low. So it has taken, let us say, some like a fall time. As you can see, there is a little bit difference that we are going to get on the output side, and this output side is TP H to L, that is high to low, and this is the difference that you will see whenever we are seeing from the input to output. Similar to that, for high to low, let us say for low to high, this is going to low to high. So what is happening, you will see there is a little difference and then only my output is going low to high. Understood? Similar to that, we have B input and A output. So if B is input, same way it will work. High to low it is going. So high to low it will come as output also, but with a little bit delay. And this is what just now we saw in the dynamic like characteristics for 1.2 volt. Similar to that, 1.5 volt and other voltage levels. There are different tables. I am not populating here, otherwise it will become very complex. Okay. So let us talk about now circuit diagram. Like how does it look like? How do we make the circuit? So let us say we have some system one which is having, let us say, microcontroller logics, okay, and we have system two which is, let us say, going to go to my I to C line or I square C lines or any like SPI signal, or let's say RS232 signal, or maybe it can go to some gate of the MOSFET where we need little bit higher voltage at the gate. Okay, so there are a lot of things. Okay, so let us say what happens is direction pin, if we just talk about. Okay, so direction pin is telling that low determines B port to A port direction. Okay, so this is bit they have changed it here completely here and there. So if direction is low, direction pin is low, that is ground, it tells you that it is going to B port to A port direction. And if direction is high, so my direction pin is low, then it will be B to A, and my direction pin is high, then it will be A to B. It means, now let us see. We have VCC A, so let's say it is 3.3 volt. We have VCC B, let us say it is 5 volt. Now I am going to set my direction pin to ground. So you can see direction is connected to ground. It means it is going to work from B to A. Okay, so B is my input. Okay, so this is my input logic and this is going to be my output logic. So this output is going to go to the microcontroller. So this particular IC is configured in such a manner that B side is working as input and A side is working as output, and this logic, whatever the logic signal that will be coming at B input will be transferred to A output to the, let's say, microcontroller, any other parts that we have there in our system A and system B. That I gave you just one example. Okay, let's talk about so this was unidirectional. Now if you want to like set it to A to B, what will you do? Let us say A should be input, and B should be output. So in that case you have to just make sure one thing, direction will be set to VCCA. Okay, so it will get connected to my VCCA pin, so it will go high, and this is how it will start working from A side to B side. That is, A will be working as input and B will be working as output. Okay, now how we can make it bidirectional? So for bidirectional thing, what we can do is, instead of connecting this direction pin to high or low permanently, we can control it through some IO signal. So GPIO of a microcontroller we can utilize to do the same job. All right. what we can do is we can control this particular direction pin through one of the IO signal of our, let's say, microcontroller. So whenever it is set low, let us say low, then it will be working from B to A, and whenever it goes high, then it will be start working from A to B. Okay, so first time it will be working, let us say, B as input and A will be the output and similar to that, A will be input and B will be output. But you have to make sure that whenever the direction pin is changing, that time there is no signal flowing from A to B or B to A. Okay, so you have to make sure the input is, or like, A pin and B pin are totally free, there are nothing flowing in the signals, and you, while you are setting the direction. Okay, and similar to that, why it is pull up and pull down is used is to make sure that it is not in unknown state. Okay, so that's the thing that we have to have. Now pull up and pull down will be required only for 74LVC1 T45. It will not be used for, or it will not be needed for 74LVCH, LVCH1. Okay, this is not requiring any things. Good, and this is all about description of bidirectional logic level shifting. So you can see we have direction control pin as high, then system 1 data to system 2, so A to B. Okay, A to B. Similar to that, when direction control is low, my system 2 data to system 1, that is B to A. So this is very simple, that has been told in the data sheet as well. And when IO pin are like high geode mode, like if basically it is data is not available right now, we are into high impedance mode, at that time it will consider the system is getting ready or it will be on hold. Okay, so why don't we quickly, hope you have very good understanding now how to configure the channel for input to output or output to input, and how to set the input voltage level and output voltage level. Let's say you needed a 3.3 volt, so 3.3 volt you will get supplied to VCC1 or VCC A pin, and you needed here 5 volt, so you will give a supply of VCC2 at 5 volt voltage level. So there are a lot of voltage translator that are available. It can be of different, number of channels. Let's say one channel, that is also called as single channel, then dual channel or dual bit or 2 bits. It can be also having 4 channels or 4 bits, it is called as. It can be as high as, let's say, 8 channels, which will be having a 8 bit or 8 lines will be there. Similar to that, we have 16 channels or 24 channels. So these days, like lot of different configurations of voltage labels or buffers are coming into picture. So let's quickly one example, see one example for each one of them. So this is the single bit dual supply voltage translator. So you can see I'm just giving you an example of a part number so that you can take this as a reference and you can extend the same concept to find another part for yourself, for your suitable application, based on the like a speed or cost that you will be requiring. There are a lot of other companies that is there, but I'm giving you one of the part for your reference. So 74LVC1T45GW is the part number for single bit dual supply, and this is the part pin configuration that you can see. We have A to B. That's all. Just now we have explained completely. This particular session was there on this particular series only, or this particular part number only. Coming back to dual bit or 2 channels. Okay, so 2 channel, you can see 1A, 2A or 2 channels are there, and we have 2 outputs also, 1B and 2B, and similar to that we have one direction pin, and we have supply voltage as VCCA and VCCB. Okay, so this is how 2 channel will look like. So you just have to change the part number to 2. Okay, so 74LVC2T45DC. This is the pin configuration that you can see. We have 2 channels like 1A, 1B and 1A going to 1B and 2A going to 2B, or similar to that it will be opposite direction based on the direction pin voltage level setting. Okay, if you talk about 4 channels, so 4 channel means also called as like 4 bit. Okay, so 4 bit voltage level translators, or it can be also working as voltage buffers. So in that case, we have A1, A2, A3, A4, sorry, this is not Y, this is YA4 B4. Okay, so this is working as this is actually a unidirectional. So you can see we have output enable pin, so you have to just keep here enable logic, and A1 will go to YB1, A2 will go to YB2, and A3 will go to YB3. And similar to that, one channel is there in the opposite direction, B4 will come to YA4. Understood? There are a lot of other part numbers. If you want, you can always look which all will be having I mean one side input and another side output. And similar to that, based on direction pin or something like that, if it is available in the IC, then you can have like direction setting, and this can start working as input, this can start working as output. But just I am giving you a very simple example of an IC which is 74LVC 4T 3144-Q100. So this is automotive uh, compliance, so it can be utilized in automotive application as well. And this is the pin configuration that is actually used. You can see VCC A side and VCC B side. Okay, and you have these three as input and three as output, and similar to that, this is one is input and this will be output. And you have OE pin, which is output enable pin. So basically whenever this goes low or it is pulled down, then only this will be in working condition. Otherwise, if you pull it up, then it will be suspended or it will be shut down. So you can see OE bar means it is active low. Active low means whenever you give a low logic at this point, the IC will be active. That's the meaning of active low. So active low is actually very easily identified by seeing the pin name itself. So if it is OE bar or EN bar, enable pin bar, then it is active low. If it is just EN, then it will be active high. Understood? So you have to give a high logic to enable the IC, and you have to give low logic to enable the IC. So that's the very basic understanding of circuit design as well. If you want to confirm this with datasheet, you have to always look into the datasheet for proper understanding whether it is really true or not. Okay, but this is the standard practices of any circuit design. Coming back to, let us say, one part I have taken for 8-bit also. So 74LVC8T 245, and this is going to have 8-bit or 8 channels. So as you can see, we have A1 to A8. So these are, let us say, my inputs, and B1 to B8, let us say these are my output. And as you can see, we have output enable pin, so which will be logic low, then only it will start working. So the IC will be in working condition or in active condition whenever it is in start whenever it is in low logic level. The very beautiful thing is it has a direction pin as well. So this direction pin will set the input to output also. So if you want to make this one as input and this one as output, then also this can work on based on the direction pin that will be set. Okay, for one of the channel, if you want to see like how does one channel looks like, so only one channel, you can see A1 to B1, it is shown properly based on the output enable pin and direction pin. So direction pin can change, like let us say right now it is input, this is output. So direction pin setting opposite side, let us say right now it is low, then it becomes high, low to high. The direction of pin I mean input to output will be changed. Okay, and you have two supplies, which is VCC A side and VCC B side, which will be working as system A and system B. So similar to that, all other channels are having same configuration. So you can have a very beautiful look here in package diagrams. We have A1 to A8. These 8 pins can act as a input output, or B1 to B8 can also act as a input to output based on the direction pin that is set, whether it is high or whether it is low. And we have two ground pins and one ground pin this side also, and we have two voltage level pins and one voltage level pin this side. So both has to, let us say this is my first side and these two are my second side. Understood? So whatever the voltage logic level that you want to put, that you can put. So hope you have a very good understanding by now what is the voltage level logic transfer, logic level transfers or level shifters or voltage translators, and what are the different aspects that we need to take care of while incorporating this voltage level or voltage level shifters in between two signals. Okay, So if you do have any questions or any queries regarding this basic building block of our very big system circuits, you can always put down your comments in the comment box, and we shall be able to give you answers as soon as possible to our best approach.